So I'm very happy to introduce Brian Collier, Riverside, California Riverside. Talking of these bundles, the Slodowy slices, and convex cocompact subgroups of Riemann.
Great. So thanks so much to the organizers and to Nigel for being working so hard over the last 50 years to give us all a great reason to come to Miami. So my talk's going to mix some of the things we've seen before and maybe some of the things you'll see in the next talk. It'll involve nilpotents like in the last talk. It'll also be about geometric structures, manifolds like in Anna Wienhardt's talk yesterday. Okay, great. So first, let's kind of set some notation and recall some things. So apologies if, well, one, you already all know this probably, and two, you've seen it 3 times now. So S is going to be a closed surface, just a topological object of genus greater than or equal to 2. G is going to be a real or complex semi-simple Lie group. For the beginning of the talk, it'll be complex, and then we'll focus on a specific real form of type A. And so the non-abelian Hodge correspondence connects this moduli space of Higgs bundles and the character variety of representations of the fundamental group of the surface into G up to conjugation. Okay, I'm just describing how this works because I want to kind of say some specific things later on. So it takes a polystable Higgs bundle, and being polystable is equivalent to being able to find a Hermitian metric on the bundle out of which I can produce a flat connection, which has holonomy in the group G. So I take the Chern connection plus the Higgs field plus its adjoint. Okay, this is something I think many of us are familiar with. Okay, and I will stick with vector bundles in today's talk. So now the main question or main theme of today's talk is when can we say something about the geometric properties of the holonomy representation associated to a Higgs bundle? Okay, so this correspondence involves solving some PDE, which it's hard to actually write down a solution. So it's very hard to, in general, to say something concrete about certain properties of the representation from the Higgs bundle. We heard from Anna yesterday that there were these special classes of representations where the individual points, the representations, were of particular interest. So when can we probe some of that information with the Higgs bundle? Okay, so the first example, which is a huge success, appears in the original paper on Higgs bundles. For this very specific Higgs bundle, so it's it's very kind of an easy first example you write down because it's align bundles and everything that you can write as somehow a matrix, but it's also like the most important example of the Higgs bundle. So I take k to the half plus k to the minus a half, and I take this Higgs field, where I'm thinking of 1 as a map from k to the half to k to the minus a half twisted by k. And in this case, Hitchin solved the equations. And the solution to the equations was the same information as a metric of constant curvature on the surface in the conformal class of your Riemann surface. Okay, so this means the associated representation is the representation into SL2R in this case, which uniformizes the Riemann surface you're on. Okay, so that's a great first success to our theme. And unfortunately, this and a slight generalization of this is one of the only times you can get such information out of the actual equations. Okay, so in the title of the talk, there's this Slodowy slice. So let me tell you about the Slodowy slice, which is just a Lie theoretic thing. The Slodowy slice is a slice through a nilpotent element of a Lie algebra, which is a slice. It's transverse to the G. Okay, so how do you construct these things? So it's going to use a theorem from Lie theory. And it's called the Jacobson-Morozov theorem. Okay, so for G complex right now, there's a version for when it's real, but I'm sticking in the complex case. For the moment, the Jacobson-Morozov theorem says that the set of conjugacy classes of nilpotent elements in the Lie algebra is in bijective correspondence with the space of conjugacy classes of homomorphisms from SL2 into the Lie algebra. Okay, and these homomorphisms are either the zero map or injective. So we can really think of them as SL2C subalgebras. So in particular, how does it work, or what does it say? It says that if I start with a nilpotent element F, then there's a way of completing it to an H and an E, such that F, H, and E define a subalgebra of G isomorphic to SL2. Or F is zero, and in which case you get the zero map. So what's the Slodowy slice? The Slodowy slice through F, I guess I'll call it SF, is F plus a vector space, VE. So VE is the kernel of add E from G to G. So since I've completed my nilpotent to an SL2, I think of my Lie algebra as an SL2 module, and I take F plus all the highest weight spaces in this representation. Okay, so this is a slice through the nilpotent orbit given by F. So for example, for SL2, there's only, well, we just take the standard generators, F, H, and E. F is 0, 0, 0, 0, 1, 0, and H and E are as given. The kernel of add E is just the span of E. Okay, so the Slodowy slice in this case is just I take my constant nilpotent F plus something in the span of E. Okay, and what makes the Higgs bundle at the top so important, and so at least for this talk, is that the Higgs field is a constant element in the Lie algebra. So the bundles are cooked up so that the Higgs field has this constant nilpotent element of the Lie algebra, makes sense as a global object on the Riemann surface. Okay, so what is now the appropriate generalization of this Slodowy slice for SL2C Higgs bundles? Well, the Higgs bundle version is I'm going to take the same bundle. I'll take my F, which is again this global object now, a section of the endomorphism bundle of E twisted by K, plus something in the span of the kernel of add E, but for that to be a right kind of bundle object, it shouldn't be a constant, it should be a quadratic differential. Okay, great, and this is the other case where, I mean, the generalization where we know all of the answers. No, we don't. So, in this case, these Higgs bundles are exactly the ones that describe all representations in maybe we call Teichmuller space, or the representations which uniformize all Riemann surfaces. It's just that the metric you get is not in the conformal class of the Riemann surface you're working on. This quadratic differential tells you which one it is. Okay, great. So this is the big success, and now I'm going to try to generalize this idea of this Slodowy slice to arbitrary nilpotents and ask some questions about it. Okay, so you just heard this in the last talk, but I'm going to say it again. So, right, we said the Jacobson-Morozov theorem tells me about SL2 subalgebras. So here my G is SLN, and nilpotent elements up to conjugation are the same thing as partitions of N. So again, I'm just going to recall you how that works because the notation is very different. Luckily, I'm not going to draw Young diagrams because if I would have been drawing the transpose of the previous talk. So we won't have to deal with that confusion. But if I write N as a partition, so I write N as a sum of di times I, where I goes from 1 to N, and my I think of di as the multiplicity of the number I, so it's something that's greater than or equal to 0. So let me just spell this out because it's always confusing. So this is 1 plus 1 plus 1 d1 times plus 2 plus 2 plus 2 d2 times, and so on. Okay, and so how do I associate a nilpotent to such a thing? This is what the Jordan decomposition theorem is. So every nilpotent is conjugate to Jordan standard form. This should be a D1, D2, Dn, where Ji is this standard I by I Jordan block. Okay, so that's how I go from the Dadabov partition to a nilpotent, and then I can complete that to an SL2 subboundary. Okay, so let's just see what happens in some small cases. So for n equals 3, there's 3 is 1 times 3. This is, we've seen, is the principal nilpotent. So in this case, F is 0, 0, 0, 1, 1. And what is the SL2? So these boxes are supposed to label these 3 parts that are in bijective correspondence. Well, I complete it to H, which is 2, 0, minus 2, and E, which is 0, 2, 0, I'm sorry, 2. Okay, so that's the principal one. There's another one, and so there's 3, which is 1 times 2 plus 1 times 1. Okay, so this is one non-trivial Jordan block, so it's 0, 0, 1, 0, which is conjugate to that nilpotent matrix. And I chose this one so that the eigenvalues of my H are decreasing. So my H in this case is 1, 0, minus 1, and my E is this one. Yeah. Oh, transpose. Okay. Great. Then the last one, of course, is 3 is 1 plus 1 plus 1, and that is 0 in SL3, which of course you cannot complete to an SL2. Okay, so for each of these cases, what are the highest weight spaces? So I'm trying to, describe this Slodowy slice, so I need to know what the highest weight spaces are for each SL2. Okay, so here they are. The highest weight spaces for bracketing with this guy are matrices of this form. There's x's on one above the diagonal, and there's a y at the top. And what are the highest weight spaces for this? Well, let me actually not write the transpose so we can see it. For that matrix, well, anything upper triangular will get somehow. Okay, anyways, anything here will automatically get killed. So those are all independent, the matrix elements. So you have a B, a D, and a C. And on the diagonal, the condition is that you have A there, and then it's traceless, so you better put minus 2A there. Okay, so now what is the Higgs bundle analog of the Slodowy slice for each of these nilpotents? So this one you're probably very familiar with. These are Higgs. I'm going to take the bundle to be K plus O plus K inverse. And the reason I want to do that, well, for many reasons, but one of them is I want my F, this nilpotent, to make sense again as a global endomorphism of the bundle twisted by K. Okay, and now I'm going to add things to that in highest weight spaces, and the type of objects I add are now sections of bundles. These are again quadratic differentials, and the one that goes all the way back in this top right corner is a cubic differential. Okay, good. What about the other case? Well, here's the type of Higgs bundle that I want to consider for the other nilpotent, the Slodowy slice for the other nilpotent. So the key important thing is that so that F makes sense as a global endomorphism with the bundle twisted by k. So I'll take k to the half plus O plus k to the minus a half. And now the Higgs field is going to be F, which is this one down here, plus things in highest weight spaces. And now these things in highest weight spaces are holomorphic sections of some bundles, exactly determined by what's showing up here. Okay, so I can modify this first example. That meant I was supposed to write something. I can modify the first one by sending E to E tensor by a line bundle, whose cube is trivial. Okay, so nothing changes in the above formulation except for I tensor everything by cubed root of the trivial bundle. Okay, all the sections are the same sections of the same bundles. The point of me doing this is like the freedom I have that will keep these ones still allowed to be one, so that it's always F. Okay, but now how can I modify the second one? The only thing I need to preserve is this one here. So that means I can say L k to the half plus, I'm going to just write it, L minus 2 plus L k to the minus a half. The only thing that needs to be the same are the two things on the end. Okay, and now everything is the same except for now beta, which is a map from here to here, is a section of L cubed k to the 3 halves, and gamma is a section of L minus 3 k to the 3 halves. Okay, and this degree of L is not doesn't have to be 0 in this case, but its absolute value is bounded if you want to consider stable Higgs bundles. Okay, and we'll see what that bound is as we go along. Okay, so this is kind of the general, so the way this general Slodowy slice works. Yeah.
Is it possible to modify that so it's not a direct sum, or is that not allowed?
It's not allowed, and maybe you'll see exactly what how the general thing works. The thing I'm allowed to modify the bundle by is determined by the centralizer of the SL2. That's the thing which, well, commutes with, in particular, F. And anyways, that'll live in the G0 piece of the Lie algebra, so that'll only modifies the summands in SL. Okay, great. So the general data is you take, well, remember, here's the Slodowy slice. I take F plus the kernel of the raising operator. And the key important thing is that H acts on the highest weight spaces, well, with eigenvalues, and so the highest weight spaces decomposes into add H weight spaces. And the centralizer C of the SL2 acts on each one of these graded pieces of the weight spaces. Okay, and so the way this general Slodowy slice works, this is just to try to give you a feel, and I've given you more examples, and we'll kind of work with examples throughout the talk, it's a map from a bunch of data. What that data is a holomorphic C bundle, where C is the centralizer of the SL2, and a bunch of sections, psi j, which are sections of the associated bundle I get by using my C bundle and the highest weight space at weight j, twisted by k to the j over 2 plus 1. And out of that parameterizing data, I build an SLNC Higgs bundle. Again, this works for G, where I do something to the bundle determined by the SL2. And then that bundle is exactly built so that this F, that is the player in the game, makes global sense as a one-form valued endomorphism. And the way that these psi j's are cooked up is these are exactly the things I can add to this object as holomorphic sections in highest weight spaces. And this, yes?
Is the harmonic form always diagonal with respect to the EC space?
No, it's not. So you'll see that in our example, because this is exactly what the Hitchens section is, which would mean, okay, you'll see that in the example, but that's not the case. And so what this means is that I can like modify the bundle by my EC bundle, and in principal bundle terms, you're like multiplying the. Anyways, the bundle comes from an H bundle, where H is, I guess, the exponential of my little h in my SL2, and I'm multiplying the transition function from that torus bundle with the transition functions of my holomorphic C bundle. Okay, but it's pretty concrete in many different examples. Okay, so the example again, what happens when you take the principal SL2 or principal nilpotent? Well, this is exactly what the Hitchin section is. This isn't like even a new formalization. This is how Hitchin described the Hitchin section. In this case, C is just one of the defining features of the principal nilpotent is that its centralizer, the centralizer of the principal SL2 is exactly the center of the group. Okay, so the C in this case is the center of SL and C, and the Slodowy slice is, well, the union of all Hitchin sections. Okay, so you take this bundle, and what you can do is you can twist it by an nth root of the trivial bundle. That's the freedom. Doing that doesn't affect F as being a global endomorphism twisted by K of this bundle. And then what I do is I add holomorphic sections. I guess I should go up just to make it clear. In this case, this bundle, this is the center. So the way the center acts on anything is the trivial. And so this is just the trivial bundle. And what I'm left with are holomorphic sections of powers of K. Okay, so anyways, you get holomorphic differentials, you get exactly the Hitchin mix. And these representations of holonomy in SL and R, and right, so now you can ask, well, what are their interesting properties of these representations? This is exactly kind of how Anna motivated her talk yesterday, and a question that was asked in this Lie groups and Teichmann theory paper. This is a great construction and tells me about this interesting set in the character variety, but it doesn't tell me much or anything really about the geometry of the representations in these components. Okay, so then Francois Laborie basically developed this notion of Anosov representations in order to answer this question. What are the geometric properties of these class of representations? So in particular, and I'm going to kind of cop out exactly like I guess Anna did, the consequence of the work is that every Hitchin representation is discrete and injective. And it's more with this ... this word Anosov, but I'm not going to define what that is in this talk. And then, so that's a big, important step. And then Guichard and Wienhardt, building on generalizing results of Goldman and Choi, showed that these Hitchin representations are all holonomies of geometric structures on certain compact manifolds. Okay, so now I have two questions that I would really kind of like to understand better. The first one is that this Slodowy slice describes to me these special components or special set of representations for the principal nilpotent or principal SL2. Are all of the representations in all Slodowy slices have some generalized property like this? I mean, the kind of easy kind of thing to say, are all of the representations associated to these Slodowy slices Anosov? So there's some evidence for this, which maybe you'll hear about in the next talk, for basically the way these higher Teichmuller spaces in general are described with Higgs bundles is the Slodowy slice. And so the answer is yes for that special class of nilpotents. But in general, I have no idea. And then another important question, which is very different, I guess, than the principal case, is the principal case is wonderful because it describes a whole component in the character variety for a real group. So in particular, the image you get does not depend on the Riemann surface you're working on, right? If I chose a different Riemann surface and looked at the image of the under non-abelian Hodge, I'm just reparameterizing the Hitchin component in the character variety. But that's completely unclear now for these general ones. So my question is, how does the image of the Slodowy slice depend on the Riemann surface you chose? Okay, so the dream answers are yes to the first one, and it doesn't for the second. I'm not going to present that to you today, but what I am going to do is give you some evidence that I like of recent work to the first one. Okay, so here's the theorem, which is joint with Zach Virgilio. Every component of the Slodowy slice associated to the partition n+1 is 2 plus 1 plus 1 plus 1 plus 1 plus 1, as far as you can go, contains representations into SU1n, which are convex cocompact. And in rank 1, this is a rank 1 group, this is being Anosov. Okay, so every component, at least, of this very specific Slodowy slice at least contains these Anosov representations, or these, let's just say, convex cocompact representations. And it turns out, from what I'll tell you about, what the SU1n locus of this Slodowy slice is, it implies that every component of the SU1n character variety contains Anosov representations, or contains convex cocompact representations. And for SL3C, we just saw there were only 2 nilpotents, right? There were not 0. There's the principal one, and then there's this one. 3 is 2 plus 1. So this says that every component of every SL3C Slodowy slice contains these geometrically interesting representations called Anosov representations. Okay. So any questions on kind of the content?
How does it one partition?
You'll see. It doesn't. It's okay. You'll see. Okay. Okay, good. So let me just remind you about complex hyperbolic space, just as definition. So SU1n, so this statement is also true for PU1n, but I'm going to stick with SU1n, so I write everything with vector bundles for ease. Complex hyperbolic n space is my model is going to be the projectivization of, I'm going to have a Cn+1 with a Hermitian inner product of signature 1n. And it's going to be the projectivization of all vectors in C1n whose norm is positive. So these are the projectivization of positive lines. And its boundary, well, is how can a positive line degenerate? It can become isotropic. Okay, so the boundary of complex hyperbolic space is the set of isotropic lines. And what does it mean to be convex cocompact? Well, it's like a tamer version of this just acting discretely, as we saw earlier in the week. Okay, so it means it acts it's convex cocompact if it acts co-compactly on the convex whole of the limit set in the boundary of the hyperbolic n space. Okay, so before the boundary, the limit set was like could become space filling or something like this. This is a much tamer version of it. Okay, now, but what can I do if I know my representation is this convex cocompact? Is I know from, I guess, what we heard earlier in the week, is that the representation acts properly discontinuously, one, on all of complex hyperbolic space, and also on the complement of the limit set in the boundary. Okay, so the second theorem is that from the Higgs bundles in describing the Slodowy slice, we can describe those quotients. Okay, so let me just give you a theorem in quotes at this point, and then hopefully make it more precise later. So the theorem is for representations from theorem 1, so SU1n locus of the Slodowy slice for that specific nilpotent, the quotient of complex hyperbolic n space by the action of the fundamental group and the quotient of the complement of the limit set in the boundary by the fundamental group are explicit fiber bundles over the Riemann surface, and the fibers are respectively complex hyperbolic space of one less dimension and boundary of complex hyperbolic space of one less dimension. So this one is this one, and this one is that one. Okay, and maybe as a remark, I'll say that for SU12, well, then the boundary is complex hyperbolic, then the fiber is complex hyperbolic one space, which is a disk, and the other one is a boundary of complex hyperbolic one space, which is a circle. So we get disk bundles and circle bundles over the surface, and this corollary one above was proven a while back by Goldman, Kapovich, and Lieb by constructing complex hyperbolic structures on disk bundles over the surface in every Toledo window. And it'd be very interesting to kind of tie together. I mean, their construction is very much cut and paste, like synthetic geometry in whatever, using a lot of complex hyperbolic geometry. These methods are completely different. It would be interesting to kind of tie them together. Okay, great. So that's kind of where we're going. Let me tell you now a bit more. So let me just remind you, the key thing is this nilpotent element in SLN plus 1, so that, anyways, I can do 1 comma n, which is 2 plus 1 plus 1 plus 1. Okay, so this is the opposite of this subregular one. This is the one that's one below this is like the minimal nilpotent one. Okay, and I have some hope that this kind of technique generalizes to minimal nilpotent orbits, but anyways. Okay, so let's tell you what is the Slodowy slice in this case. Okay, so here's the SL2. It's just like before. This is like the smallest nilpotent you can get. The F is all the way down here. Here's the H, and here's the E. What are the highest weight spaces? So their matrices of the form B, A, B. Let me just get my C and D right. D, C, and E. So maybe I'll just put a box around this one. A is in GL n minus 1, and the trace of A is equal to minus 2B. Okay, and everything else is so B is just a number. C and D are vectors in Cn, or Cn dual, if you like. One is one, one's the other. Okay, so anyway, let me just make it clear. This is a 1 by 1, n by n, 1 by 1. Okay, that's the kernel of bracketing with that guy. Now, what is C? C is the centralizer of the SL2, which I'll move over here. C, well, it's lambda A, lambda 0, 0, 0, 0, 0, 0, where the determinant of A is lambda to the minus 2. Okay, that's exactly the group which in SLNC, which centralizes the whole SL2. It centralizes H because it's in like the levy associated with that parabolic. And since this is lambda and this is lambda, it clearly acts trivially on here and there. Okay, so these are the kind of key important Lie theoretic things which I need to build this Slodowy slice. So what's the Slodowy slice? Let me start out by not twisting by this C object. What I'm going to do is just take k to the half plus n minus 1 copies of the trivial bundle plus k to the minus a half. And the Higgs field looks like this, right? I add the 1, which makes global sense, and then I add holomorphic sections of appropriate bundles where I'm working in this splitting. Okay, and now I can modify this by a C bundle, but what is C? C is like GLNC, right? A GLN minus 1C. So when I modify it by a C bundle, I'll put LK to the half plus V plus LK to the minus a half where determinant V is L minus 2, and the rank of V is N minus 1. And now I'm just going to kind of write it more symbolically. This map alpha is a map from V to itself twisted by K. The 1 is a map here, which goes from LK to the half to LK to the minus a half twisted by K. And then there's these betas. Then there's this delta, this gamma, and then the last guy in the upper triangular bit is a quadratic differential. Okay, so these are the Higgs bundles which describe the points in the Slodowy slice. Maybe I should just say delta is a holomorphic section of LK to the 3/2 V dual, and gamma is a holomorphic section of LK to the 3/2 with an inverse tensor V. Okay. So now the question, the statement of the theorem was that the SU1n locus of this Slodowy slice has these interesting representations, which I can say something about. So what's the SU1n locus? So an SU1n Higgs bundle is an SLN plus 1C Higgs bundle of the form, which has this extra symmetry where the bundle decomposes as a line bundle plus a rank n bundle. And with respect to that splitting, the Higgs field is off diagonal. Okay, so I'd represent that schematically just like this. And the key point is that if E phi is polystable, then the metric, Hermitian metric solving the equations for an SU1n Higgs bundle splits as a direct sum of a metric on this line bundle plus a metric on this rank n bundle. And with respect to that splitting, if I take the signature 1n Hermitian metric, which is HM plus just negate the second one, this is in fact a parallel. This is parallel with respect to the associated flat connection. So this is what makes this symmetry give me the fact that my holonomy representations are in fact in the group SU1n. The metric on the flat bundle, if I change the sign on one of the summands, is a signature 1n Hermitian metric, which is preserved by the connection. Okay, so here are the Higgs bundles in this special Slodowy slice. What is the SU1n locus? Well, the first thing to note is that surely, I mean, definitely alpha has to be 0 and beta has to be 0. Okay, so the line bundle M, that's special, has to be one of these two line bundles. Okay, so what that means is that alpha has to be 0, beta has to be 0, and gamma has to be 0, or delta has to be 0. So it's and of this statement. So one of the gamma or deltas has to be 0. So let me just again write those schematically. That's k to the half L, 1, k to the minus a half L, V. So this is the case when gamma is 0, so I look like this. And then delta, so in this case, right, this rank n bundle is my W, and this one is my M. And in the other case, which one is the line bundle is flipped. So k to the 1/2 L, V, k to the minus 1/2 L, Q2, 1, gamma, these are the other ones. Okay, so this is the SU1n locus of the Slodowy slice for that nil. Okay, so what I'm going to do is specialize just a little bit more, just like what I'm going to do is set the quadratic differential to 0 and rewrite them. And what you get are these special types of Higgs bundles associated with variations of Hodge structure. Okay, so the first case when gamma is equal to 0 is just a variation of Hodge structure like this. In the second case, when delta is equal to 0, you get a variation of Hodge structure like this. And okay, so I rewrote them. Let me just say, let's see, delta goes to here, m is k to the half L. Okay, and so a relatively straightforward computation shows you that polystability forces the degree of m to be bounded between minus g plus 1 and g minus 1. Okay, and the Toledo invariant of this SU1n Higgs bundle up to normalizing it however you want is the degree of m. So the Toledo invariant doesn't come from the nilpotent. It comes from the fact that the centralizer of this SL2 is GL1, and so that is the data of a line bundle, and it's the degree of that line bundle that is changing the Toledo invariant. Okay, good. So just to now, the statement of the theorem we actually proved is that the representations associated to these Higgs bundles for all degrees of m are convex cocompact. Okay, so this is all points in the SU1n locus of this special Slodowy slice are given by these special variations of Hodge structure, and they all have this extra interesting geometric property, namely they act on the symmetric space, the complex hyperbolic space, in this convex cocompact way. Okay, some remarks. Okay, I said the degree of m was equal to the Toledo invariant. In particular, these representations are Fuchsian, meaning they factor through an SL2, a uniformization of the Riemann surface, if and only if the degree of m is g minus 1 in absolute value. This is the case which corresponds to maximal representations, or representations which factor through SU11 put inside SU1n, a holomorphic disk in complex hyperbolic space. And so that's one example. And the other example occurs when the degree of m is 0. This is the case where you factor through like the other hyperbolic disk, which is Lagrangian. Well, I guess in CH2 is Lagrangian, okay, but whatever. This means you go into the from the fundamental group into SU12, which you then include into SU1n by a standard way. And for all other values of the degree, these representations are not Fuchsian. So you have no reason to expect them to be Anosov from before. Okay. Any questions? Yeah.
When you say convex cocompact, you mean as a quotient of the n multiplied by the dimensions of the compact?
No, I mean that the representation acts co-compactly on a convex set in complex hyperbolic space. So that convex set is the convex whole of this limit set, which is on the boundary. Yeah, in each of these cases, I've been drawing the picture in real hyperbolic 3 space because I can't draw it above. If the representation factors through, say, SL2R inside SL2C or SO21 inside SO31, then you preserve the boundary. The limit set is the boundary of a hyperbolic disk inside, and the convex whole is a hyperbolic disk. And the quotient again is your hyperbolic surface.
But is it ever that it acts co-compactly on the full ball?
No. Except for, of course, when it's SU11, so that's, I guess that's the point. Your group is kind of too small for that to happen. Great. So let me now tell you about how we prove this and some previous related results. So the first previous related result was a theorem I proved with Nicolas Tolosana and Jeremy Trullis. So most of this paper was focused on maximal representations into SO2n and describing these geometric structures associated to them. But we also said, okay, well, here's some other Higgs bundles. They're of this form. And this trick we played to show that we could construct these geometric structures from Higgs bundles which originated, this idea is originated with, at least to my knowledge, with David Baraglia in his thesis, which is what Steve gave me to read when I started my thesis. So that trick we used to show that these Higgs bundles defined these defined representations, which were holonomies of these special geometric structures, worked for these other class of Higgs bundles that were looked like this. So we could show that we got some holonomies of isotropic line structures in R23 on circle bundles over my Riemann surface. But we had no idea if the representations had any of these nice geometric properties. We had no kind of worries. We had no idea if these representations were Anosov. It was just this trick works to construct them with these Higgs bundles too. And wouldn't it be great if we could understand them? Well, we couldn't, but somebody else did. So recently, Simeon Filip focused on exactly variations of Hodge structure of this form when beta, when they're variations of Hodge structure, when beta is equal to 0. And the key property that makes everything work is this 1 out here. So these turn out to be points in some Slodowy slice for SO5, but I won't tell you about that. So what Filip proved is that when beta equals 0 above, the associated representations with those variations of Hodge, those Higgs bundles, did indeed have this Anosov property. And he was able to, so because they have this Anosov property, there's an associated geometric manifold associated to them, and which comes from this Guichard-Wienhardt construction. And he showed that the geometric structures we constructed up here were exactly the ones that you get from the Guichard-Wienhardt machinery, using the fact that the representation is Anosov. Okay, so I think this kind of work is pretty amazing progress. And the question that I raised at the beginning, when can we use something about a Higgs, when can we say something concrete about a representation from a Higgs bundle? Okay, so, and our theorem that I've been telling you about is really that we adapt Filip's methods from SO23 to this case SU1N. And again, I'm hopeful that it'll kind of apply to points in Slodowy slices for a minimal number. Okay, so let me tell you a bit about how that works. So I'm going to focus now. Remember, we kind of started this general Slodowy slice thing. Now we're just going to focus on these very specific Higgs bundles, where the degree of M is between 0 and G minus 1. And the associated SU1N Higgs bundle is the following thing. It's M, that's my rank 1 thing, plus my rank N thing, which is a direct sum of an N minus 1 thing with a rank 1 thing. Okay, and with respect to that decomposition, my Higgs field looks like this. Okay, great. So those are the objects we're going to be considering. And the key ingredient for what we're going to do, or one of the key ingredients, is that this is a fixed point of the C-star action. So the metric is diagonal in this holomorphic decomposition. Okay, so since this metric is diagonal, the data describing my flat connection, or my flat bundle, is, well, the flat bundle, it has a parallel signature 1n inner product on it, and that's equal to minus the metric on HV, the metric on HM, minus the metric on the last piece, right? The way I got the signature 1n thing was I just put a minus sign on the metric on this block. But that metric on that block splits as a direct sum metric on a line bundle in a rank n minus 1. Okay, and now with respect to this splitting, I guess this should probably be the star and this one should not be. Oh no, I've rearranged the way I've written it. So in this splitting, V plus M plus MK inverse, the flat connection, which is the Chern connection plus the Higgs field plus the adjoint has this very kind of special variation of Hodge structure form. And a key property is that H1n restricted to these two pieces, nope. Oh, the key property that I want to tell you about is that H1n, that signature 1n metric, restricted to those two subbundles has signature 1, n minus 1. Okay, so, oh, I clicked the wrong one. So here's the theorem we actually proved, which is theorem 2, describing the quotients of these. So here's, I guess, an answer to your question, Carlos. What is the quotient of CHN, or the ball, by the whole group? It's a CHN minus 1 bundle over the surface. So the fibers are non-compact. Okay, so we describe those geometric structures very explicitly. So the representation associated to one of these variations of Hodge structure above, when I take the quotient of CHN by the representation, I get a projection map to the surface, and the fiber, well, is 1, it's a CHN minus 1, but it's pretty a concrete CHN minus 1. It's the set of projectivization of the set of positive vectors inside this rank n subbundle, right? So the restriction of the metric here has signature 1n. So if I look at only the positive vectors in here, then that's a CH, and I projectivize, that's a CHN minus 1. Okay, so the set of vectors in this piece of the Hodge bundle is describing to me the fibers of this quotient. And similarly, this quotient of the boundary, but when I remove the limit set by the action of the group, is the same bundle where instead of positive vectors, you put isotropic vectors. Okay, so that's pretty concrete. From the Higgs bundle, you can describe what the geometric structures are. And here's the idea of the proof, which I think is, I'll tell you a little bit about it at least. So the first parts are easy. Flat sections of, so I'm going to pull back my flat bundle to the universal cover. Flat sections of that pullback are identified with vectors in the fiber, which is C1n. And for each vector u in C1n, if I think of that as a flat section, I get to decompose it as a sum of different pieces where I project onto each of the pieces of each summand. So remember, my bundle is equal to V plus M plus MK inverse. And I can project onto each piece. Okay, so the data of a vector gives me a flat section, and I can project that onto each of the pieces. And so for each vector u, which is positive, which is not negative, so either isotropic or positive, so that's something either in the boundary of complex hyperbolic space or in the interior, we consider the following function. F u is a function on the universal cover, which is going to take the norm squared of the projection onto this factor right here. Okay, so that's something you can do. It turns out this function sees everything. It's exactly the thing which is responsible for all of the results I've told you about in Filip's work, where he has a version for SO23, but this is how you translate it into this thing. Okay, so let me tell you some facts about this function. So there's a different function on the universal cover for every non-negative vector. And here's a theorem. Again, we translated it into this SC1n thing, but the main ideas come from this work of Filip. So for all vectors u in C1n, which are non-negative, x is a critical point of that function if and only if the function vanishes. So if and only if the projection onto the last part in the Hodge bundle is 0. And for each u, fu has at most one critical point, and that critical point is a non-degenerate, well, minimum, because the function vanishes. It's definitely a minimum. Okay, so these actually are, not hard to prove bits. Then he says a bunch more. Well, okay, this next one, I guess. If I look at the space, if I assume my vector is positive, then this function has exactly one critical point. So this function really does attain its minimum. And if it's isotropic, then it may attain its minimum or it may not. And then he proves some strong exponential growth of this function, namely the function's value. So if you have this positive vector, then you have this unique critical point. This is the part of the theorem, and you can look at another function, which is the distance you are in the hyperbolic plane from that critical point. And what he proves is there are these universal constants, C, D, and alpha, such that this function is growing faster than that exponential of that distance. And this last part, I'm not going to tell you anything about, but is the key to prove this Anosov property. Okay, so again, let me just not tell you about this part now, but I just wanted to mention is that this understanding of the kind of growth of this function is compared to the distance from your unique critical point is a very important concept. Okay, so let me show you the easy points and how we're going to make essential use of all of the assumptions that or many of the assumptions that we use. So the definition of the function seems quite kind of innocent, but it's amazing how much mileage you get out of it. So let's just recall that this is my Higgs bundle I'm working with, and this is the decomposition of the flat connection. Again, I have a flat section of the bundle pulled back to the universal cover, and I get to write that as a sum, where each sum end is the projection onto each of the pieces. And some key properties are, if I assume my vector is non-negative, then since the signature on V is negative and MK inverse is negative, it means that the projection onto the middle piece is nowhere vanishing. Because the norm is supposed to be positive or non-negative, and if its projection onto the middle piece was 0, then it would definitely have to be negative. Okay, so this is our function. Let's compute its derivative. Okay, well, it's the derivative of some norm squared with respect to one of the pieces in the Hodge metric. Okay, so I get to use the Chern connection to differentiate here. And since I assumed my vector was associated to a flat section, when I differentiate a vector here, and I look at the projection onto the last piece, I get exactly this term here. Okay, so I get to replace these guys by -1, something that's nowhere vanishing, applied to something that's nowhere vanishing. Okay, so what you get is this expression here, and the key thing is that, well, 1 is nowhere 0, and this vector u's projection onto the middle factor is also nowhere 0. Okay, so this derivative is 0 exactly when umk inverse, the projection onto the last factor, vanishes. Okay, and that's exactly when the function is 0. And you compute the Hessian, and it's like twice the norm squared of 1 applied to the middle projection. Okay, also, it's positive. Okay, so the critical points are non-degenerate minima. Let me just see what I have here. Okay, so now I end with this thing. My question to you is, if I fix x in the universal cover. So before I needed to fix a vector and I had a function from the universal cover to R. Okay, now I'm gonna fix a point in the universal cover and ask, what are all of the positive or non-negative vectors which have this X as a critical point? Well, the answer is they're exactly the vectors U, which are contained in the fiber X in the first two summands. Because the critical points are exactly when the function is 0 and the function is projection onto the last factor. Okay, and so this is exactly the fiber of the geometric structure. Okay, so it's like the fibers of this geometric structure are the collection of critical points of these functions at that point, or the collection of vectors whose critical points occur at the same point X. It has this very, like, I don't know, Kempness feel in how it works. And I'd be interested to try to understand this type of connection more. Okay, so I'm not going to go on further and describe for you the geometric structures, but it's they're pretty canonical exactly. Maybe I'll just tell you the punchline is this function sees the image of the developing map of this geometric structure. In particular, since there always exists a unique critical point when the vector is positive, it means the developing map is a diffeomorphism onto the whole complex projective n space for the positive case. So that's how you get to relate this geometric structure with the quotient of the action on the whole CHN. Okay, so I'll end there. Thanks for listening.
Question? Does this kind of Kempness functional with Filip, does this work somehow for higher rank groups as well? Or?
So he did it for a rank 2 group. He did it for SO23. But in that process, he very much used this real symmetry. So let me just go back. Here. So what he applied it to were these types of Higgs bundles. And what the function was is you took, so now the flat bundle is an R23 bundle, and you take the norm squared of the projection onto the last piece again. The key thing is the thing that maps into the last piece is nowhere vanishing. But since there's this real symmetry, you look at real things, so there's a real form, which is a conjugation, which takes the point here and its conjugate is a point over here. Okay, so anyways, if you tried to do this example, but broke the symmetry that this bundle was the dual of this bundle, then his argument wouldn't work. You would be working in like SU23 and something breaks. So just to say, he worked in SO23, which is a rank 2 group, but you can't just naively make it work in SU23 by the same trick.
Yeah, do you have any idea as to whether any of these representations, any of these variations of Hodge structure come from, variations of Hodge structure that you get in algebraic geometry?
Yeah, so for the ones I just told you about, no, I guess they don't because they're complex for sure. They're SU1 and
no, but they could be direct factors of a complex variation of Hodge structure could be a direct factor in that.
Yeah, so I have no idea for the ones that I was telling you about today, but the motivation of Filip's work was exactly he had this SP4R, which is SO23, variations of Hodge structure coming from hypergeometric equations, and the key property defining them was that there was this 1 right here. So it was, the Hodge numbers were 1, 1, 1, 1, 1, 1, 1, and one of the pieces in this was nowhere vanishing. So he does this not on compact curves, he does it on on the base of this variation of Hodge structure. But he sets it all up so that it just kind of works in general for these types of Higgs bosons. But the main reason he was interested in it, from my understanding, is exactly to understand. So for these special types of variations of Hodge structure, there were these conjectures about the Lyapunov exponents of their holonomy. And there's a conjecture by Eskin, Kronsevich, Moller, and Zorich. And part of the paper he did was proving that conjecture for exactly these variations of Hodge structure. And anyways, so he does a lot in that, but the point that I can understand the best was my translation of it to you today.
Okay. Any other question?
And so you raised this question at the beginning about whether the Slodowy slices depended on complex structure.
Yeah.
Do you have any intuitive feeling about that? Any results?
I have 4 examples of families where the answer is it does not. They're the magical ones where you describe these higher Teichmuller spaces. But in general, no. Maybe the answer is no in general, but when you kind of restrict to some real forms, the answer might be yes. I just don't know. But for example, if you looked at what is the SU1N locus of these Slodowy slices, then they look like the things that I was just describing, which you could hope, to describe whatever topologically, plus adding this quadratic differential. And I set that quadratic differential 0, so I get a variation of Hodge structure and the metric would split and all that game. And then, it seems not crazy to think that as I move my Riemann surface, that corresponds to somehow changing that quadratic differential in the parameterization. But I don't know anything more than that.
Okay, so since the program's a bit tight, so it's Planck, Brian.